Now that we have talked about hash functions, it is a good time to talk about passwords and password cracking. So databases always leak, and hashes of the passwords leak too. But even recently, in Turkey and in the world, many databases of important companies leaked, and we again realized that people don't know how to store passwords and how they can be cracked. So let's talk about a little bit about how to store passwords and how to crack them. So we don't store the passwords, but we store their hashes. So we talk about this because cryptographic hash functions have primary resistance. So if you keep your passwords in the database or in a file, and the file or the database leaks, people capture the passwords. But if you keep their hashes, they have to find the image of these hashes. So in this way, if you keep the hashes, leakage of the database should not leak the passwords because we are using primary resistant hash functions. But of course, the attacker can still try to break the password, try to capture them. There are two ways of doing it. The generic two attacks especially. First one is called dictionary attack, and the second one is called exhaustive search or brute force attack. So let's start with dictionary attack. We always hope that a dictionary attack was something like this, but unfortunately it is not. But I would really want to try it after the pandemic ends. But anyway, so dictionary attack works as follows. So just assume that a database leaked and you captured a lot of hashes. So now you want to find the passwords of these hashes. So even before the database leaks, you can do the following. You can pre-compute the hashes of common words on a dictionary, their combination with numbers, their combination with each other, and so on, and list all of the hashes, then sort them. So when the attacker captured when the database leaks, you also capture the hashes, and you have a sorted table of pre-computed hashes. So you compare both of the tables to see if they have common elements. So if they have, since you already pre-computed the hashes of your tables, this means that you already know the password. So this is called a dictionary attack. So as you can see in this scenario, first you do the pre-computation. For instance, you assume that people still are using MD5, and actually people do that. So you compute the MD5 hashes of a lot of possible passwords, which are again a combination of words with numbers, with some special characters, and so on. And for instance, you calculate like 8 terabytes of hashes and keep them sorted in a hard drive. You also, now, at some point in time, a database leaks, you capture the database, and you look and see that they were keeping the MD5 hashes of the passwords. Now you sort it to, and by just comparing the sorted tables, which is very easy, since they are sorted, you can just find the passwords of users if you have those passwords in your dictionary. So it is as simple as that. So in order to overcome this attack, what we do in practice is to use salts. So salts are just randomly generated numbers like 32 bits and something like that, but they're generated when somebody creates a password. So instead of a hash of a password, we store the concatenation of the password with the salt that is randomly generated at the time of account creation. And so here I'm saying the salt is a randomly generated public value, but of course you are not publicly announcing this value, but you just keep it in the database as a plain text. This is why I say it public, because if the database leaks, people know the salt values. So since if we keep the hashes of these concatenation of values, now the dictionary attack would not work, because in the dictionary attack, you are calculating the hashes of some possible words and combination with numbers and so on. You never create a dictionary for some values concatenated with 32-bit random value, right? So in this scenario, now the passwords are kind of masked with the salt, because if two users have the same password, since we would be generating two random values, their salt will be different. So hashes of their password will be different too. In the previous scenario, when like 10 users have the same password, breaking one would also give you the other 9 because all of the hashes would be the same. But in this case, salts will be different and the hashes of the password will be different. So this actually overcomes the problem of dictionary attack if the salt is large enough. If it is short, like for instance 8 bits, then the attacker has to generate 2 to the 8, which is 256 different dictionaries, and perform the dictionary attack again. So we recommend at least 32 bits of salt. So assume that this is what we are doing. This is the measure we take. Some people only do that, which is still not enough, because now the hackers can perform an exhaustive search attack. An exhaustive search attack is something which you guess. When a hash and the salt value is obtained, which are in the database, and when it leaks, you obtain these values. You calculate hash of every possible short password and check if the hashes are identical. So if you assume that, for instance, the user has chosen a 6-character password, you just take the hash of every 6-character password concatenated with the salt value and check if the hashes matches. If it does, then you capture the password. So here, this is what is important. I say here short passwords, but now we have to give a scientific definition for this short. So how long, how many characters are considered short actually depends on the current technology. And years ago, people considered the computational power of CPUs. So they said that 8-character passwords are secure, but nowadays we have really good CPUs and even better GPUs. So 8-character passwords are not that good. So let me explain it to you why. So just assume the 8-character passwords. English alphabet has 26 letters. So if you generate a password with only using small letters from English alphabet, you have 26 to the power 8 different possibilities for passwords. So your password space is this. I wrote it as a power of 2 for you to see the how hard it is, because I mentioned that for a GPU we can perform 2 to the 33 hash operations in a second. So this is nothing for a single GPU. You can just capture it. You can try all of these passwords in a few seconds just using a single GPU. So this is why when you are generating passwords, the web pages also says you to use capital letters. So if you use also capital letters, now you have 52 characters. So the search space considerably increases when you compare it to this value, right? But we also say that you should add some numbers, but we have like 10 numbers. So this is why as a character, it increases a little bit. The password space increases to 2 to the 47. But if you use all of the printable characters in the ASCII table, this is the whole number of possible passwords which have length 8. So as you can see, 2 to the 52 is not such a huge number. Again, I told you that we can perform 2 to the 33 password searches using a single GPU. So if you have like thousands of GPUs, you can search the space in a few seconds. So as you can see, 8-character passwords are not secure. Moreover, we can search the space in a clever way. For example, users select easy to remember short passwords. They always never use more than 2 special characters. Actually, we have some ideas about what kind of passwords people choose, but I don't want to mention them here because it would be unethical, and people's password can be a target in this way. So I'm just skipping this part. So if 8-character passwords are not secure, what we can do, we can force users to choose like 12 or 13-character passwords, but that will be very hard to remember. It will be very hard for people to use those passwords. So instead, we can do the following. We can slow down the hash computation speed for the attacker so that it takes longer time to try every 8-character password. So how can we do it? Instead of using the hash value of a password, repeatedly use the hash output as the hash input. For instance, I take a number which is a power of 2. In this case, 2 to the 8, I guess. No, 2 to the 13. Yes, this is 2 to the 13. 8,192 times. So this means that you have the password, you concatenate the salted, you take the hash of it. Instead of storing the hash in the database, take this hash value, put the hash function again, and calculate the second hash value. Repeat this process more than 8,000 times, and the resulting hash value would be your the value you keep in the database. Why this is important? Because now, I mean, for even when you are logging in, you enter your password, and the web server has to perform 8,000 many hash operations for letting you in. This is why, some logging operations might take some time on slow computers, but this also makes the attacker's jobs more than 8,000 times harder, because now for every password they try, they have to take 8,000 many hash functions. So in the previous case, for instance, assume that the attacker can try all of the 8-character passwords in a single day. And you take this countermeasure, it will take more than 8,000 days for the attacker to break the system. So this is why you have to slow down the hash computation speed. I think this was the default value in Linux systems, but it was, I last checked like 5 years ago, so it might be increased in the current versions. So I don't know. So let's move on to some other usages of passwords. I want to talk about password-based key derivation. This is important because it is very hard for users to choose their own cryptographic secret keys. For instance, if you want to use AES, it is hard for somebody to generate 128 bits which are random. So instead, what we can do is the following. We can choose a password and compute many hashes of it, and the resulting value can be used as the secret key. So password-based key derivation functions actually uses this idea. This PBKDF2 is kind of a standard. It is included in many RFCs and in many applications, let's say. It is also a part of RSA Laboratories' public key cryptography standards. So it works like this. This function takes the following values. It takes pseudo-random function. In our scenario, we will put a hash function here. It takes your password, salt, C, and decay length. So C is actually the number of hashes that you are going to perform, and this length value is actually the number of bits you need for the secret key. Okay, so if you want to use AES 256, this number should be 256. So yes, here actually the definitions are given. One thing we need to mention here is this. The pseudo-random function is a pseudo-random function of 2 parameters. So consider the hash function. A hash function actually takes a single input, right? For SHA-1 or SHA-2, you will put the message and take the output. But in this case, we will put 2 parameters to it. Actually, one of them is the message, and the other one would be the key. So let's see how that works. Okay, so here is the detailed explanation of the password-based key derivation. So the whole key are actually the concatenation of TIs, because you might need a very long key. For instance, if you are using RSA 4096, then you will choose this number 4096, but a hash function produces 256 bits. So your first T1 value for SHA-256 will be 256 bits. So you have to concatenate a lot of hash outputs to obtain the whole key you want. So let's focus on a TI value. So it takes the input as password, salt, C, and I. And it performs the following XOR operations. Here, int 32BE, actually the representation of I as a 32-bit integer value using the big endian notation. Okay, so you are repeatedly actually computing the pseudo-random function with these parameters. As you can see, it takes two inputs. One of yours is password and the other one is salt and this value. Okay, so let me give you a concrete example. WPA2 uses password-based key derivation function 2. And these are the following parameters. So in your modem at home, when you choose an SSID and the password for your wireless communication, this is what happens. The passphrase and SSID, if we go back to our definition, are used as password and the salt. So your SSID is your salt. As you can see, it is not a secret value. Here it is chosen as 4096. So the hash function SHA-1 is repeated 4000 many times. And the output's key length is chosen as 256 because we are going to use AES256. Okay. And as you can see, as the hash function, instead of saying SHA-1, we say HMAC SHA-1, which we are going to talk about. This is a message authentication code. So in this case, SHA-1 is used as a keyed hash function. I told you that in here we said that it takes two parameters, PRF, and the two parameters are your password and your salt concatenated with the ith value. So in your wireless modem, this password is the password you choose. This is SSID concatenated with I. So similar thing also is used in Winrar. So Winrar uses this, but instead of 4000, they chosen this number as 32,800. So trying to break a Winrar password is a lot harder than trying to break a WPA2 password. So our analysis showed that Winrar passwords longer than 8 characters are secure. You can confidently use them. So we actually performed brute force attacks on Winrar password using a GPU, which is a little bit old nowadays. But we observed that if you use only numbers, small letters and capital letters, and if your password length is 6 characters, it takes for us around 40 days to capture your password. So if you use your Winrar password for a file, and if it is short, this is good news, you can recover it. But for security, you need more. We showed that increasing the character length actually exponentially increases the attack time. Of course, here it doesn't contain all the printable characters, but if you use all of the printable characters, and if you choose your password as 6 characters, it takes 1 year. So you might think that this is still long, but this is for an old GPU and for a single GPU. So if you have like tons of GPUs which are modern, it will take a few days to break this password. So increasing it to 7 characters, it is again a huge number, but on the internet, if millions of people gather together, they can still perform a brute force attack. This many, this length passwords. But as you can see, when the password length is 8, performing an exhaustive search attack requires 13,000 years. So if you have 13,000 GPUs, it will take a single year. So it is still in the reachable range. So you should still consider choosing a password with like 9 characters or longer. So final thing, so we all talk about password hashing here, and we always mention SHA-1 and SHA-2, but the question is, can we get a better function for just password hashing? So this is why there was a competition. The idea was that password hashing is everywhere. there was an established standard to fulfill the needs of modern applications and to best protect against attackers. So this password hashing competition was initialized by Jean-Philippe Ormosson in fall 2012. The competition web page is here. You can obtain all the information about the competition from this web page. It had received 24 submissions. 9 finalists were announced in December 2014, and in July 2015, Argon 2 was announced as the winner. So if you want to store hashes of your passwords, instead of using SHA-2, Argon 2 actually would be a better choice because it won this competition. But let's focus on other finalists. 4 other finalists are received special recognition. I listed them here. They are Catena, Lyra 2, Magma, and Yescrypt. I know that some alternative cryptocurrencies are using Lyra 2 for their proof of work state. So for mining of these coins, you need to perform Lyra 2 operations. So these are some important password hashing algorithms that you might use in practice.